Hi, and welcome back to the Guilligum Electronics Baseline PIC Assembly Language tutorials. In this lesson, we'll see how to make your code more modular or reusable, while dealing with some of the baseline PIC architecture's limitations. As always, it's a good idea to refer to the PDF version of this tutorial, which you can download for free from the Guilligum Electronics website, to fill in any details that this video skims over. In the last lesson, we blinked an LED by using a simple inline delay loop on the smallest PIC there is, the 10 of 200. Now a delay is a pretty handy thing, so you probably want to use code like that in other projects. And you'll probably want the delay to be able to be longer or shorter than half a second. So we'll turn that delay code into a more general subroutine that can be used in other programs. You'll almost certainly want to be able to use bigger PICs, and this is where the baseline PIC architecture shows its ugly side. The first PICs weren't designed to be able to have much program or data memory, so to squeeze in more memory, Microchip had to add concepts such as banking and paging that we'll take a look at in this early lesson, because you can't program baseline PICs in assembly language without being aware of some of this stuff. Mid-range and high-end 18F PICs aren't as bad, but they still have some of these issues. Of course, you can avoid having to know these details by programming in C, and that's perfectly fine. But if you want to really understand PICs, you need to know this stuff. So let's do it. Before we move on to bigger PICs, we'll take a quick look at subroutines. If you've done much programming at all, you'll be aware of subroutines, which are called functions in languages such as C. Basically, they allow a block of code to be run, or called, from more than one part of your program, instead of having to repeat blocks of inline code, and they make the calling code more readable by hiding details. So let's start with the flash and LED code from the last lesson, and move the delay loop into a subroutine. Adding some comments. And of course, you will have created a new MPLabX project for this lesson, like we did in the last one. The start of each subroutine needs a label. And then to call the subroutine, you use the call instruction, which pushes the program counter onto the stack, then jumps to the subroutine. The baseline PIC stack is only 2 deep, so although you can call a subroutine from within another subroutine, you can't nest the calls any deeper than that, so be careful. When the subroutine is finished, it needs to return to wherever it was called from, and that's done with the retlw instruction, which pops the program counter back off the stack and returns a literal value in W. If your code doesn't need to return a value, you're out of luck, because retlw is the only return instruction on baseline PICs. You'd usually just return a 0 if you're not returning some specific value. Okay, that's great. Our main loop code is a bit more readable, but a subroutine that can only generate 500 millisecond delays isn't all that useful. To make it more general, we can make it delay some multiple of 10 milliseconds, and then specify that multiple when we call it. We can pass the delay length to the subroutine by loading it into W. So we'd call the delay routine like this: 50 for a 500 millisecond delay. Then we modify the delay subroutine adding a third counter to count multiples of 10 milliseconds. Saving W to that counter, and adjust the inner loops to make them total 10 milliseconds. Now that we have a variable length delay routine, we can use it to flash the LED with something other than a simple 50% duty cycle. We could, for example, have it on for only 20% of the time. So be on for 200 milliseconds, then off for 800 milliseconds, by updating the main loop, like this. And I'll just update the comments at the start of the program to reflect that. When I build the updated program, the LED still flashes once a second, but it's on for less of the time. Much more interesting. Now we'll move the code to a slightly bigger PIC, the 12F509. It still comes in an 8-pin DIP package, but it has 6 I/O pins instead of 4, so now all of the 8 pins are connected. We'll still be blinking an LED connected to GP1, so the circuit's pretty much the same as before, just with the 12F509 instead of a 10F200. To build this circuit with the baseline PIC training board, make sure you remove the 10F200 from the 10F socket. Then insert the 12F509, provided with the board, into the top part of the 12F16F socket, and close the jumper next to the LED labelled GP1. Every other jumper should be left open. The 12F509 has 4 times as much program memory as a 10F200, 1024 words instead of 256. That presents a bit of a problem, because the GoTo instruction only has 9 address bits, which means it's limited to 512 addresses, which is known as a page. The 12F509 has 2 pages of program memory. Which page to jump to is specified by the PA0 bit in the status register. Setting PA0 selects the second page, and any subsequent GoTos or calls will jump there. Even bigger baseline PICs also have a PA1 bit, which allows them to select up to 4 pages, for a total of 2048 words of program memory. You don't need to set these bits directly, because there's an assembler directive, PageCell, which does it for you. We'll see how it's used soon, but first I need to highlight another baseline PIC limitation. The call instruction only has 8 address bits, and that means the entry point of every subroutine has to be placed in the first 256 words of a page. So with our program arranged the way it is, there's a danger that if the main loop becomes longer than 256 instructions, the delay subroutine will end up outside that 256 address limit, and we won't be able to call it. Of course, that can't happen on a 10F200, which only has 256 words of program memory. But it's a risk with bigger PICs, like the 12F509. You could rearrange the code so your subroutines are at the start of memory, but the same problem comes up if the subroutines get too big. The solution is to add what are called subroutine vectors to the start of memory, or the start of any page really, like this. The main code calls the vector, which is always located in the first 256 words on a page. And then a GoTo instruction jumps to the actual subroutine code, which can be anywhere in memory. At the start of the program, we then need to jump past the vectors to get to the main code. Now, if something really can be placed anywhere in memory, we shouldn't be too prescriptive. We should let the linker place code wherever it sees fit. And we can do that by putting each section of code into its own code section, and only specify an address for the reset code, because execution has to start at address 0. The rest we don't care about. Mind you, anywhere really does mean anywhere, so I better make sure the correct page is selected before every call and GoTo, which is done with PageCell directives like this. You don't need them on absolutely every single call and GoTo though. We know, after calling the delay subroutine once, that the page it's on will still be selected when it's called a second time, because there's no other call or GoTo between those calls. so we don't need another page cell here. Now we can change the code to run on a 12F509. By updating the list and include directives, the reset vector, because it goes at the end of program memory, and the 12F509 has more memory. And we also need to update the configuration to specify that we want to use the internal RC oscillator. The 10F200 doesn't give you a choice, but the 12F509 gives you more oscillator options, which we'll take a look at in a later lesson. We also need to tell MPLABX that we're using a 12F509, and you can do that by clicking on the project properties icon in the project dashboard and change the device to pick 12F509. The new device, with more program and data memory, appears in the project's dashboard. When you build this program, you find it works the same as the 10F200 version. The extra data memory in the 12F509 leads to a similar problem. In baseline PICs, the instructions which access registers, such as the move instructions, only have 5 address bits, which means they're limited to 32 register addresses. That's okay on the 10F200, which only has 8 special file registers and 16 general purpose registers for storing data, leaving 8 addresses unused. The 12F508 adds more general purpose registers by using every possible register address. To allow baseline PICs to have more data memory than that, Rocketship split the register file into multiple banks of 32 registers each. The 12F509 has 2 banks, with the special file registers mapped into both banks, so you don't need to worry about which bank is selected when you're accessing a special file register. That's not true on mid-range PICs though, so be careful there. The first 9 general purpose registers are also mapped into both banks. They're shared between banks, so they're called shared registers. You can access them regardless of which bank is selected. The top 16 addresses in each bank are different. One bank is used to access one set of 16 bytes of data memory, and the other bank accesses another 16 bytes. These are called banked registers, and to use them, you need to make sure that the correct bank is selected first. Only one bank can be active at once, and the active bank is selected by a set of bits in the file select register, or FSR. Only bit 5 is used on the 12F509, because there are only 2 banks to select from. The biggest baseline PICs also use bits 6 and 7, which allow them to have up to 8 register banks. But, similar to paging, you don't need to set these bits directly, because there's an assembler directive, bankcell, which does it for you. To see how to handle banked data memory, we'll go back to flashing the LED with a 50% duty cycle, using a shadow register to flip GP1 every 500 milliseconds. A shadow register is the type of variable that's likely to be accessed often, from various different parts of a program, including subroutines. To make it easy to access, without having to worry about banking, we can ask the linker to allocate a shared data register for it, and we can do that with the udata shr directive, which declares a section of shared memory. Then we can simply access sgpio with no need for a bank cell. Shared registers are a limited resource though, so to avoid wasting them, we can continue to use the udata section for the delay loop counters. We don't know where the link will place this section. It could be in either bank. So, before these variables are used, we use bankcell to select the appropriate bank. It doesn't matter which variable is specified here. The loop counters are all declared in the same section, so they'll all be in the same bank. Okay, the program will now work on any baseline PIC with banked memory. That's great, but now we have this handy delay routine. Wouldn't it be great to be able to use it in other programs? You could just copy and paste the code, but there are a couple of problems with that. Your other program might have its own DLY1 or DLY2 labels, or variables called DC1, DC2 or DC3. It'd be better if the code was self-contained, external to the main program, so there's no scope for conflicting labels or variable names. We can do that by putting the subroutine into a separate file, and declaring any variables it uses within that file. then the main program doesn't need to know about them, and it becomes an independent module, called a relocatable module because it, and its variables, could be placed anywhere in memory. To make the delay subroutine a separate module, I'll first create a file for it. Right-click Source Files, then New, Other, then select Assembler, and we want an ASM file, Next, and call it Delay 10, and Finish. I'll also rename the main file. Now I can copy and paste the subroutine code out of the main program and update the comments. It's easiest in this case to just copy the whole thing and delete what's not needed. It's best to get rid of the list directive to avoid the assembler complaining if you later use this module in a project with a different processor, but the include should stay. The module should define only the variables it uses, the delay counters in this case. There's no need for configuration, RC calibration, reset vectors, or any of the main program, just the subroutine itself. And we can drop the label from the code section. Okay, so what makes this a module? How does it advertise that it provides a delay routine? The answer is the global directive, which tells the linker that this label, and only this label, the entry point for the subroutine, should be accessible from outside. And I'll just add another comment to explain that, although we're including a file for a specific PIC, this module can be used with any baseline PIC. Then, in the main program, we can delete the whole subroutine section. And update the comments. We can also delete the delay loop counters. They're not needed in the main program anymore because they're defined in the module now. Finally, add an extern directive to tell the linker that this label is defined externally. Basically, global and extern work as a pair. You use global in the external module and extern in the main or calling program. Hit Make and Program, and both files are assembled, linked together, and programmed into the PIC. The LED blinks yet again. That's enough blinking LEDs for now. In the next lesson, we'll read a push button switch and see how to debounce it. See you then.